Firstly, let's review the result of the example we discussed in last lecture. We have a uniformly charged spherical surface with radius r. The total charge carried by the surface is q. We calculated the value of the electric field and then find the potential in space. Now, let's compare E and V as shown in the figure. We notice that in the region outside the surface, the electrical potential is a function of r, while the electric field is a function of r squared. Inside the surface, the potential is constant everywhere, while the field is zero. Today, we are going to explore the relationship between E and V further. We have known that how to find the potential if the electric field E is given. What if the situation is reversed? How can we determine the electric field if the electric potential is given in a certain region? As we know, the differential potential difference dV can be expressed by this one. Let's assume that the electric field has only one component Ex. Then the dot product of E and ds reduces to Ex dx. Therefore, Ex equals minus dV over dx. This equation shows that the x component of the electric field equals the negative of the derivative of the electrical potential with respect to x. For the y and z components, we have the similar equations. Hence, the electric field is a measure of the changing rate of potential with position. If an electric field has a spherical symmetry, the dot product of E and dr reduces to Er dr. In this case, dV equals minus Er dr. Therefore, Er equals minus dV over dr. Using that example again, the potential outside the surface V equals Ke Q divided by R. Because V is a function of R only, the potential function has a spherical symmetry. Applying the equation, we have the value of the electric field outside surface. Er equals Keq divided by R squared. Also, inside surface, the potential is constant. The field is zero since the changing rate of the potential is zero. In general, the electric potential is a function of x, y, and z. Thus, the electric field components Ex, Ey, and Ez can be found from V as the partial derivatives as expressed by these equations. So, if there is no change in the potential along some axis, the component of the field along this axis must be zero. If the potential is constant over a surface, we call it equipotential surface. If a charge is moving along an equipotential surface, the change of the potential is zero. So, from this equation, the vector E must be perpendicular to the vector ds because of zero potential difference. That indicates the equipotential surfaces must always be perpendicular to the electric field lines passing through them. Here you may find the patterns of equipotential surfaces from these figures. The equipotential lines are the dashed blue lines and the electric field lines are the brown lines. Obviously, the equipotential lines are perpendicular to the field lines everywhere. For example, for a field due to a single point charge, the potential changes only in the radial direction. So, in this case, the equipotential surfaces are a family of spherical surfaces concentric with a point charge as shown in the figure B. These surfaces are perpendicular to the field lines which are directed radially. So far, we have spent a lot of time in exploring the properties of electric field in free space, where there is no other objects in the region. If we put some objects into space, how about the interaction between the field and the object? We are going to explore this topic